Inductive reasoning. Type of reasoning that forms a conclusion based on the examination of specific examples is called inclusive reasoning. The conclusion formed by using inductive reasoning is conjecture, since it may or may not be connected. No. Inductive reasoning is the process of reaching a general conclusion by examining specific examples.
Let me give you example of inductive reasoning. Example number 1, inductive reasoning. Using inductive reasoning of predict a number. Use inductive reasoning to predict the next number of each of the following list. Letter A, 3, 6, 9, 12, 15. Letter B, 1, 3, 6, 10, 15. Solution. A. Each successive number is 3 larger than the preceding number. Thus, we predict that the next number in the list is 3 larger than 15, which is 18. Letter B. The first two numbers differ by 2. The second and the third number differ by 3. It appears that the difference, since 10 and 15 differ by 5, we predict that the next number in the list will be 6 larger than 15, which is 21.
How to use inductive reasoning to solve an application. To solve an application using inductive reasoning, use the data in the above table and inductive reasoning to answer each of following question. First question. If a pendulum has a length of 49 units, what is its half-length? Table, a pendulum has a period that is the square root of its length. Thus, we conjecture that a pendulum with a length of 49 units will have a period of 7 heartbeats. Question number 2. If the length of a pendulum is quadruped, what happens to its period? In the table, a pendulum with a length of 4 units has a period that is twice that of a pendulum with a length of 1 unit. A pendulum with a length of 16 units has a period that is twice that of a pendulum with a length of 4 units. It is appear that a quadrupling the length of a pendulum double its period.
Conclusions based on inductive reasoning may be incorrect. As an illustration, consider the circle shown below. For each, all possible line segments have been drawn to connect each dot on the circle with all the dots on the circle. As shown on the illustration, at the first circle, it contains 1 dot. Then the second circle, it contains 2 dots and get connected from the first dot to form a line. And on the last circle, 1 more dot added and get connected to the first 2 dots and form a shape of a triangle.
Good day everyone. Now I am going to discuss about deductive reasoning. Another type of reasoning is called deductive reasoning. Deductive reasoning is distinguished from inductive reasoning in that is the process of reaching a conclusion by applying general principles and procedures. Deductive reasoning is the process of reaching a conclusion by applying general assumption, procedure, or principles. Example, use deductive reasoning to establish a conjecture. Use deductive reasoning to show that the following procedure, a number that is 4 times the original number. Pick a number, multiply the number by 8, add by 6 to the product, divided by the sum by 2, and subtract by 3. Let me give you an explanation about the solution. Let n represent the original number. Multiply by 8, add by 6 to the product, and divide by 2, then subtract by 3. Now, n is equals to 8n plus 6 over 2. Then we have 4n plus 3. Then subtract by 3. We get the 4n.
Inductive reasoning versus deductive reasoning. In example 6, we analyze arguments whether they use inductive or deductive reasoning. Example 6. Determine types of reasoning. Determine whether each of the following arguments is an example of inductive reasoning or deductive reasoning. A. During the past 10 years, a tree has produced plums every other years. Last year, the tree did not produce plums, so this year the tree will produce plums. B. All home improvements cost more than the estimate. The contractor estimated that my home improvement will cost $35,000. This my home improvement will cost more than $35,000. Solution. A. These arguments reach a conclusion based on a specific example, so it is an example or inductive reasoning. B. Because the conclusion is a specific case of a general assumption. This argument is an example of deductive reasoning.
Logic puzzles. Logic puzzles can be solved by using deductive reasoning and a chart that enables you to display given information in a visual manner. For example, each of 4 neighbors, Sian, Maria, Sarah, and Brian, has different occupation: editor, banker, chef, or dentist. From the following clues, determine the occupation of each neighbors. We have 4 given clues. Number 1, Maria gets home from work after the banker but before the dentist. Number 2, Sarah who is last to get home, not the editor. Number 3, the dentist and Sarah leave for work at the same time. Number 4, the banker lives next door to Brian. Now let's proceed to the solution. From clue number 1, Maria is not the banker or the dentist. In the following chart, write X1, which stands for ruled out by clue number 1, in the banker and dentist columns of Maria's row. From clue number 2, write X2 in the editor's column of Sarah's row. We know from the clue number 1 that the banker is not the last to get home. And we know from clue number 2 that Sarah is the last to get home. Therefore, Sarah is not the banker. Write X2 in the banker column of Sarah's row. From the clue number 3, Sarah is not the dentist. Write X3 for this condition. There are now X's for 3 of the 4 occupation in Sarah's row. Therefore, Sarah must be the chef. Place check in that box. Since Sarah is the chef, none of the other 3 people can be the chef. Write X3 for these conditions. There are now X's for 3 of the 4 occupation in the Maria's row. Therefore, Maria must be the editor. Insert check to indicate that neither Sia nor Brian is the editor. Let's now proceed to the last clue. From the clue number 4, Brian is not the banker. Write X4 for this condition. See the following table. Since there are 3 X's in the banker column, Cian must be the banker. Place check in that box. Thus, Cian cannot be the dentist. Write X4 in that box. Since there are 3 X's in the dentist column, Brian must be the dentist. Put a check in that box. Now we identify what is the occupation of each neighbors. Cian is the banker, Maria is the editor, Sarah is the chef, and Brian is the dentist. If you still don't get it, let me explain it to you briefly. From clue number 1, Maria gets home from work after the banker but before the dentist. Ibig sabihin, si Maria hindi po siya banker, hindi din siya dentist. Unang umuwi yung banker, sunod si Maria, sunod yung dentist. And sa clue number 2, Sarah who is the last to get home, not the editor. So sa clue number 2, si Sarah hindi siya editor at hindi rin siya banker. Since sa clue number 1 nabanggit na mas naunang umuwi yung banker, then sa clue number 2 nabanggit na si Sarah ang huling umuwi, ibig sabihin yung banker ay hindi si Sarah. Sa clue number 3, the dentist and Sarah leave for work at the same time. Ibig sabihin, hindi rin po din dentist si Sarah. Sa clue number 1 and 2, nalaman natin na hindi editor si Sarah, hindi din siya banker. And sa clue number 3, hindi din siya dentist. So it means Sarah must be the chef. Since si Sarah na nga yung chef, at si Maria naman hindi siya banker, hindi din siya dentist, at hindi din siya chef, so Maria must be the editor. And for clue number 4, the banker lives next door to Brian. Since si Maria editor, si Sarah is chef, at yung banker ay hindi rin si Brian, ibig sabihin si Brian po ay yung dentist. Since si Sarah is the chef, Maria is the editor, and Brian is the dentist, then the banker must be Cian.
Can-Can Puzzles, an introduction. Can-Can is an arithmetic-based logic puzzles that was invented by the Japanese mathematics teachers Tetsuya Miyamoto in 2004. The noun Ken has knowledge and awareness as synonyms, hence translates as knowledge squared or awareness squared. Can-Can puzzles are similar to Sudoku puzzles, but they also require you to perform arithmetic to solve the puzzle. Rules for solving a Can-Can puzzle. For a 3x3 puzzle, fill up in each box square of the grid with one of the members, 1, 2, or 3. For a 4x4 puzzle, fill in each square of the numbers 1, 2, 3, and 4. For n-by-n puzzle, fill in each square of the grid with one of the number 1, 2, 3, and so on. Grid range in size from a 3x3 up to a 9x9. Do not repeat a number in any row or column. The numbers in each heavily outlined set of square called cages must combine in some order to produce the target number in the top left of the cage using the mathematical operation indicated. Cages with one square should be filled with target number. A number can be repeated within a cage as long as it is not in the same row. Not in the same row.
This is the example of Can-Can puzzle in 4x4 with 8 cages. Each cages has its given numbers. First cage has the number of 6 and the multiplication sign. You can simply multiply 1 times 2 times 3. Second cage has the number 7 and the addition sign. It has 2 squares and you can simply add number 3 and 4 and the answer is 7. Third cage has a given number of 2. In that cage, it has only one square. You can simply write the number 2 on that square. The fourth cage has a given number of 8 and the multiplication sign. It has 3 squares and you can simply multiply 1 times 4 times 2 and the answer is 8. Next cage is the fifth cage, which has a given number of 4 and the multiplication sign. And it has 2 squares. You can multiply the number 1 times 4 and the answer is 4. In the sixth cage, which has a given number of 12 and the multiplication sign, and it has 2 squares, you can simply multiply 4 times 3 and the answer is 12. Seventh cage has a given number of 1 and it has only 1 square. You can write the number 1 on that square. And the eighth cage, it has a given number of 1 and the subtraction sign. You can subtract the number 3 and 2, which is the answer is 1. And that is the solution of a can-can puzzle equation.
Problem solving with patterns. Terms of a sequence an ordered list of numbers such as 5, 13, 27, 44, and 65 is called a sequence. The numbers in each sequence that are separated by commas are the terms of the sequence in the above sequence. 5 is the first term, 14 is the second term, 27 is the third term, 44 is the fourth term, and 65 is the fifth term. The 3 dots indicates that the sequence continues beyond 65, which is the last written term. It is customary to use the subscript notation AN to designate the nth term of a sequence. That is, A1 represents the first term of a sequence, A2 represents the second term of a sequence, A3 represents the third term of a sequence, AN represents the nth term of a sequence.
this experiment. And the chance of winning the grand prize is by not switching strategy. Because when you switch your choice, you only have two probability of winning the grand prize. It's either you open the wrong door or open the door with the grand prize behind. Kung baga, tiyamba na lang kung makukuha mo ba yung isang grand prize or hindi kapag nag-open ka or nag-switch ka ng choice mo na buksan yung other closed door. Marilyn Vos Sevant, author of the Ask Marilyn column featured in Parade magazine, analyzed this problem, claiming that you double your chances of winning the grand prize by switching to the other closed door. Many readers, including some mathematicians, responded with arguments that contradicted Marilyn's analysis. What do you think? Do you have a better chance of winning the grand prize by switching to the other closed door or staying with your original choice? Of course, there is also possibility that it does not matter if the chances of winning are the same with either strategy.
So let us now discuss the problem-solving strategies. And one of the foremost recent mathematicians to make a study of problem-solving was George Polya in 1887 and 1985. George Polya was born in Hungary and moved to the United States in 1940. The basic problem-solving strategy that Polya advocated consists of the following. Polya's 4 steps are deceptively simple. To become a good problem solver, it helps to examine each of these steps and determine what is involved. Let us now discuss the first step, which is to understand the problem. This part of Polya's 4-step strategy is often overlooked. You must a clear understanding of the problem. To help you focus on understanding the problem, consider the following questions. First question, can you restate the problem in your own words? Second question, can you determine what is known about these types of problems? Third question, is there missing information that if known, would you allow to solve the problem?
Devise a plan. Successful problem solvers use a variety of techniques when they attempt to solve a problem. Here are some frequently used procedures. Make a list of the known information. Make a list of information that is needed. Draw a diagram. Make an organized list that shows all the possibilities. Make a table or a chart. Work backwards. Try to solve a similar but simpler problem. Look for a pattern. Write an equation. If necessary, define what each variable represents. Perform an experiment. And guess at a solution and then check your result.
Carry out the plan. Once you have devised a plan, you must carry out. You can work carefully, keep an accurate and neat record of all your attempts. Realize that some of your initial plan will not work and that you may have to devise another plan or modify your existing plan.
Example, apply polio strategy. Make an organized list. The problem. A baseball team won 2 out of their last 4 games. In how many different orders could they have 2 wins and 2 losses in 4 games? So here's the solution. Let's apply the polio's 4-step problem-solving strategy. First, understand the problem. There are many different orders. The team may have won 2 straight games and lost the last 2. Or maybe they lost the first 2 and won the last 2. Of course, there are other possibilities such as win, lose, win, lose. Second, devise a plan. We will make an organized list of all the possible orders. An organized list is a list that is produced using a system that ensures that each of the different orders will be listed once and only once. Third, carry out the plan. Each entry in our list must contain 2 W's, short for wins, and 2 L's, short for lose. We will use a strategy that makes sure each order is considered with no duplications. One such strategy is always write a W, unless doing so will produce too many W's or a duplicate one of the previous orders. If it is not possible to write a W, then, and only then, do we write an L. This strategy produces the 6 different orders shown below. So first, 2 consecutive wins and 2 consecutive losses. Number 2, win, lose, win, lose. The third, win, lose, lose, and win. Number 4, lose, win, win, and then lose. Number 5, lose, win, lose, win. And the last, number 6, start with 2 losses and ends with 2 wins. So fourth, review the solution. We have made an organized list. The list has no duplicates and the list considers all possibilities. So we are confident that there are 6 different orders.
Solve a similar but simpler problem. Here the problem. In a basketball league consisting of 10 teams, each team play each of the other team exactly 3 times. How many league games will be played? Solution. First, understand the problem. There are 10 teams in the league and each team plays exactly 3 games against each of the other teams. The problem is determine the total number of league games that will be played. And second, we use the devise a plan. Try the strategy of working a similar but simpler problem. Consider a league with only 4 teams, in which team play each of the other team only. The diagram at the left illustrates that the games can be represented by lane segments that connect the points A, B, C, and D. Since each of the 4 teams will play a game against each of the other 3, we might conclude that this will result in 4 times 3 equal 12 games. However, the diagram shows only 6 line segments. It appears that our procedure has counted each game twice. For instance, when Team A plays Team B also plays Team A. To produce the correct result, we must divide our previous result 12 by 2. Hence, 4 teams can play each other once in 4 times 3 over 2 is equal 6 games. The first step is review the solution. We could check our work by making the diagram that includes all teams. All 10 teams represented by dots labeled A, B, C, D, E, F, G, H, and L, and 1 because this diagram will be somewhat complicated. Let's try the method of making the unorganized list. The figure shows an organized list in which the notation BZ represents a game between Team B and C. The notation CB is not shown because it also represents a game between Team B and Team C. This lists the 45 games are required for each team to play each of the other team once. Also notice that the first row has 9 items, the second row 8 items, and the third row has 7 items, and so on. Thus, 10 teams required 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 is equal 45 games of each team. Place every other team. Once a 45 minus 3 minus 135 games if each team plays exactly 3 games against each opponent.
I will be discussing about the poly strategy. So, we have to determine that digit 100 places to the right of the decimal point in the decimal representation, which is the number 27. First, we have the solution. We have to understand the problem. Express the fraction 2 over 27 as a decimal and look for a partners that will enable to determine the digit 100 places to the right of the decimal point. Third, devise a plan. Dividing 27 into 7 by long division by using a calculator produces the decimal is 0. etc. Since the decimal representation repeats the digits, so repeat the digit to 59. Over and over forever, we know that the digit located 100 places to the right of the decimal point is either a 2, a 5, or a 9. A table may help us to see a pattern and enable us to determine which one of these digits in the 100th place. Since the decimal digits repeat every 3 digits, we use a table with 3 columns. So we have first 15 decimal digits of 7 over 27. We have column 1, column 2, and the column 3. So the location and the digit. In the first column, the location is 1st, 4th, 7th, 10th to 13th. Then the digit is 2. In the second column, we have 2nd, 5th, 8th, 11th, and 4th, and the digit is 5. And in the third column, 3rd, 6th, 9th. So 6, 9, 12, and 15. The digit is 9. So the third step, we have to carry out the plan. Only in a column 3 each of the decimal digit. So in the third step, we have to carry out the plan. Only in column 3 is each of the decimal digit locations evenly divisible by 3. From this pattern, we can tell that the 99th decimal digit, because 99 is evenly divisible by 3, must be a 9. Since a2 always follows a 9 in the pattern, the 100th decimal digit must be a2. So, in the last part, we have to review the solution. So, the above table illustrates additional patterns. For instance, if each of the location numbers in column 1 is divided by 3, a remainder of 1 is produced. If each of the location numbers in column 2 is divided by 3, a remainder of 2 is produced. So, thus, we can find the decimal digit in any location by dividing the location number by 3 and examining the remainder. For instance, to find the digit in 200 yet decimal place of 2 over 27, merely divide 3,200 by 3 and examine the remainder, which is 2. Thus, the digit 3,200 places to the right of the decimal point is a 5.